Hello, everyone. I'm Zikun from UIUC. Today, I will talk about removing channel feedback for next generation cellular networks. This is a joint work with Deep, Chen, and my advisor, Deepak. So I will talk a lot about channel feedback today, and I will tell you in a bit what channel feedback is. But channel feedback is an important problem in next generation cellular networks. Cellular network operators today has deployed more and more antennas at their base stations in order to increase the throughput. For example, Verizon company has already deployed 64 to 128 antennas at their base stations. However, with increasing number of antennas at the base station, the channel feedback overhead also increases. In fact, it increases linearly with number of antennas at the base station. With just 64 antennas at the base station, this channel feedback overhead can be as large as 50% of the spectrum. So think about it. Cellular network operators today pay billions of dollars in their spectrum, but 50% of them are wasted on just the channel feedback. Both academia and industry has understood the problem and proposed various solutions. In academia, many recent papers have proposed to tackle this problem. And in industry, the standard bodies 3GPP and many other high-tech companies such as Ericsson, Apple, Samsung, and others have also proposed many new solutions to decrease this channel feedback overhead and save the spectrum. However, all the ways to reduce the channel feedback overhead ends up hurting the performance of cellular networks. In this talk, I will show you how we can achieve zero channel feedback while maintaining the same performance as full feedback. So I will start my talk by talking about what is channel feedback and what causes channel feedback. Then I will show you our system called FIRE, which is an end-to-end machine learning-based technique to remove the channel feedback. Finally, I will talk about the evaluation results using public datasets and our hardware settings. So what is channel feedback? As I mentioned earlier, base stations deploy many antennas. And they deploy these antennas in order to communicate with multiple user clients simultaneously. But before sending data to these clients, base station needs to know the channel values to each client. And these channel values form a channel matrix. Base station needs to know one channel matrix for each client. Let's say these channel matrices are H1, H2, and H3. So these matrices can be measured locally at the client. Base station does not know this information yet, but it can get this information from the clients. Clients will then send these measured channel matrices back to the base station as a feedback. But this process is wasting time and resources. So if we look into this channel matrices in detail, you will find that actually base station needs one channel values from each of its antenna to the clients. So this means that the data that you send as feedback increases linearly with number of antennas at the base station. Recall that there are hundreds of antennas deployed at the base station serving many clients. This can be a huge overhead. And you need to measure this channel every few milliseconds. So with a 64 antenna base station and 8 clients, explicit channel feedback can consume over half of the throughput. This means that you are using half of the throughput to just transmit the channel feedback, while only use the other half for use for data transmission. And as number of antenna increases, the channel feedback also increases. So what can we do to deal with it? Today, I will talk about our work FIRE, which is an end-to-end machine learning-based technique to remove this channel feedback completely. With FIRE, the channel feedback overhead can be removed such the whole network resources can be leveraged for useful data transmission. And thus we achieve zero feedback multi-antenna systems. Before diving into the detail of FIRE, I want to talk about the intuition behind it. So base station knows the uplink channel from the clients to itself. what it wants is the downlink channel, which happens in another frequency and in the reverse direction. This is because US cellular networks operate in FDD mode, where uplink and downlink are different. Previous works have shown that although uplink and downlink channel happens in different frequency, they actually share the same physical multipath as they travel in the air. So the downlink channel can be treated as a function of uplink. Thus, previous works propose optimization algorithms to first derive these path parameters such as distance and angles, and then they plug in the new frequency in order to estimate the downlink channel. But in order to get the accurate downlink channel estimation, they need to be very precise in their path parameter estimations. With a very small error, such as 0.5 centimeters in distance measurements, will reduce the SNR by 10 to 20 dB. So this means that you can go from HD video streaming to just text-based browsing. What makes it more interesting is that this is actually the fundamental limitation of the bandwidth. Cellular networks operate at around tens of megahertz, and with this limited of bandwidth, you cannot accurately estimate these path parameters. So what can we do? Here's an idea. If we know where the big reflectors are, such as buildings and ground, it becomes much easier to know the path that signal will take, and I can be more accurate in my estimation. Besides, since base station is always operating at a fixed location, I can use multiple measurements to infer this environment. Our idea is to use data-driven approach with machine learning to model this physical environment. We deploy a machine learning model at the base station to implicitly learn this physical environment and predict the downlink channel. So how should we use machine learning? There are two options. First, you can use machine learning to predict the path distance and angles. But the problem with it is how to train this model. We do not know the exact and accurate path that signal will take. The second option is to directly predict the downlink channels. But the problem is this method is not accurate because it does not accurately model the wireless channel generative process. Our idea is to use end-to-end generative model to model this process, inspired by the physics level intuition that both uplink and downlink channel are generated from the same physical path parameters. We model this process using generative models. Specifically, we choose the very popular variational autoencoders, which is VAE, as our neural network architecture. VAE's encoder neural network will first take the uplink channel as input, feed it into the neural network, which will encode this uplink channel into a low-dimensional latent space. And the decoder neural network will sample from this latent space, feed it into the neural network, and then generate the downlink channel estimation. The reason why we use VAE is because it can accurately model the generative process of how wireless channels are created. In the past, VAE has already been successfully applied to a variety of generative tasks, such as text generation, image interpretation, so on and so forth. Besides, the latent space of VAE is usually disentangled and is such a natural candidate to get more insights into what the neural network has learned. And we design our loss function to be the combination of L2 loss plus KL divergence. KL divergence can make sure that the latent space is meaningful, which means that the encoded uplink channel close to each other in the latent space should not be too different. And also, we use L2 loss to enforce that the predicted downlink channel resembles the ground truth. Great. So far, I'm introduced to you our neural network architecture used to predict the downlink channel. So can we start to feed into the uplink channel and start the prediction? Well, unfortunately, it's not as simple as that. There's still one big problem left. That is, even if the environment is static, the wireless channel will keep changing. And this means that any model that you train with these measurements will be confused by this randomness and won't be able to learn how wireless channels are generated. So there are several reasons. First, this is because of the carrier frequency offsets, which is CFO, between the base station and the clients. Secondly, there is packet detection delay. So this delay is due to the time difference between the signal reaches the front end of the hardware, then it actually gets detected by the decoding chain. And the problem is, it's impossible to remove these hardware offsets and variations. What we want is one physical configuration corresponds to one channel value. Based on this, we proposed the channel transformation technique. Our key intuition is that we only care about the relative channel values. MIMO techniques only cares about the relative channel values across antennas rather than the absolute channel values. What we want is to preserve these relative channel values while still have one channel value correspond to one physical state. Note that the channel matrix has two dimensions. One is the number of antennas, as I have shown you before, and the other one is subcarriers in OFDM. The first transformation is to normalize the CFO. Since CFO at the same phase offsets across different antennas, we can divide the channel estimation matrix H by the channel values at the first antenna to normalize it. Secondly, we should normalize the packet detection delay. So if we plot the phase of the channel for antenna number 1, the x-axis represents the frequency bins, and the y-axis represents the phase value. And if we conduct a linear regression on it, we can actually get the slope value, which contains the packet detection delay on the first antenna, delta D. So that we can use this delta D information derived from the first antenna and apply it to all the other antennas to normalize these packet detection delay. Based on these transformation techniques, we find that we can eliminate the randomness and yet preserve the relative channel values. Now, let me show you the evaluation results using public datasets and our own test bed. We evaluate FIRE first on Argos dataset, which is a public dataset, and we evaluate using up to 64 antennas and users at different locations. And its deployment can be shown on the left figure. Secondly, we also validate FIRE's results on custom hardware platform using Iris radios. Before diving into the evaluation details, do we actually encode the physical information? So we conduct a simple showcase experiment. We collected channel values from the clients at 6 different locations, and we reduce these channel matrices dimension to 2 in order to plot them. As you can see, different colors represent different clients, and this figure shows intense entanglement on the uplink channel space between different clients. Then we conduct the same analysis on the latent space of VAE, and this time, different clients form different clusters. So this means that wireless channels at different physical locations actually gets mapped to different points in the latent space. So this means that we actually encode the physical information even though we do not directly train for it. Now, I will show you the channel prediction accuracy using our custom hardware platform. The x-axis represents the achieved SNR in dB, and the y-axis is the CDF value. More accurate channel estimation accuracy will deliver higher SNR. First, I plot the performance of 3 baselines. The first 2, R2F2 and OptiML, are traditional signal processing based method. And the final one, FNN, is a fully connected neural network using regression task to predict the downlink channel. As you can see, these 3 baselines roughly have the median SNR of 10 dB. And if we plot the performance of FIRE, we can actually see the median SNR gain of 1.68. So this means that Fire can deliver very accurate channel prediction accuracy and achieve very high SNR for data transmission. Next, we evaluate how Fire's channel prediction accuracy will work under massive MIMO applications. So we let the base station to beamform towards two different clients and measure the signal to interference plus noise ratio at them. More accurate downlink channel prediction will lead to more accurate beams, thus less interference between clients and higher SINR. We also increase number of antennas at the base station in order to check the scaling performance of Fire. So as you can see on the figure, x-axis represents the antenna number scaling from 4 to 64, and the y-axis represents the SINR value. So first, I plot the performance of 3 baselines. So as you can see, all these baselines have increasing SINR when antenna number goes up. This is because more antennas deployed at the base station will allow it to cancel the interference better. Then we plot the performance of Fire. As you can see, at 64 antenna case, Fire achieves the SINR of 29.11 dB, which is 1.79 volts higher than the best baseline, which is R2F2. So this means that Fire can deliver very accurate channel prediction across different numbers of antennas. And it's well suited for the massive MIMO applications. Fire is inspired by the previous works on downlink channel prediction. And we achieve higher throughput while maintaining zero overhead compared to the previous methods. One thing worth noticing is that compared to the explicit feedback, Fire achieved very similar throughput performance, but we have no overhead at all. To conclude, we propose Fire, which is an end-to-end machine learning-based technique to predict the downlink channel using generative model. And we propose channel transformation technique to normalize the randomness. It achieves very high accuracy on public datasets and our own hardware platform. We envision computational tools such as Fire will sit at the core design of the future 5G and 6G deployments. Thanks.